Greetings. This is an example of test-driven development using what I call the PolySolve example. This is a small Java program that was written by some students of mine a number of years ago, following test-driven development pretty much along the lines that are taught by Kent Beck and Bob Martin, following the sort of three rules of test-driven development, which means that we basically are not allowed to write code unless we have a failing unit test, and we try to make the tests incremental, so just enough tests to fail, and when we write code, we write just enough code to pass the test. So this example is a polynomial solver. In fact, it's a quadratic equation solver, and in this case, the software would take three inputs representing the coefficients a, b, and c in the quadratic equation ax squared plus bx plus c equals 0. And then what the application will do is, given the values a, b, and c are provided as real numbers, it will try to compute what is x, and there's two possible values for x, which are the roots of the quadratic equation. X could be any complex number. A, B, and C are real numbers. At least that's what's prescribed in the requirements for the little example program. It's expected to be a command line program. So someone types a command, polysolve, followed by three numbers, hits return, and gets the result on the screen. In this case, the application was written in Java using an IDE. At the time, was Eclipse was very popular. The unit tests were written in JUnit framework. The application is expected to be robust, which means that in the case of a equals 0, we expect it to treat that as if it was a linear equation, and therefore bx plus c equals 0, x is equal to negative c over b. If a and b are 0, we have an error condition. If a, b, and c are 0, we have an infinite number of solutions. And this basically is expected to work with values up to 15 digits of precision. So that's what sort of the constraints were on the project. And what I'm going to do is just walk through the development tests one after the other to create PolySolve. So PolySolve ABC, that's the command line. It's written as a terse application in the style of Unix command line applications. So it's very terse error messages, very simple syntax, nothing too complicated about it. And the math is well defined, well understood, especially by the students who were asked to do this. They're expected to know this stuff quite well. So the first test that was selected by this particular student was the test, imagine if there's no arguments. Imagine if someone types polysolve without putting three parameters, A, B, and C. All right. Well, that's, I guess, a reasonable test. I personally don't like starting with error conditions like that. I like to start with building up the business logic, but it's a student. They're allowed to pick any order of development they want. It's a reasonable test, so they start. So the first test they have is no arguments, and the expected result is an error message in the style of a terse Unix error message, which would say usage : polysolve ABC. That's what the error message would look like. So we basically start off, we have an empty class, there's nothing in it, and we try running the test, and it fails. You see on the bottom of the screen that the test fails. The expected result was usage polysolve ABC, but instead we got an empty string. That's the output, so we have a failed unit test. Therefore, based on Bob Martin's three rules of test-driven development, we are allowed to write some code, but just enough code to pass the current failing unit test. So in this case, the programmer writes one line of code, one solitary line of code, which is to print the message usage polysolve ABC. That's the expected result. That's the error message. And now the test passes. You'll see that after you add any change to the code, all the previous tests keep running over and over again automatically, transparently, as part of the development approach using Eclipse with JUnit. All right, so now we have one test and it passes. So that's a good step forward. we go to the second test. In this case, the programmer says, well, what if we have less than 3 arguments? We should get an error message then too. And they provide the same error message, which is usage polysolve ABC. Now this is, I guess, a reasonable test. It's certainly a reasonable error condition. But as I said, I prefer to start with business logic. This is error handling. It's got to be done, I suppose. All right, so we run the test, and remarkably, it passes. Because the error message, the expected outcome for the second test, is exactly the same as the expected outcome for the first test. And so even though we have not written any code, we have a passing unit test. So the developer is not allowed to write any code, because you can only write code if you have a failing unit test. So the programmer goes on to the third test, which yet again is another one of these error handling tests. And in this case, they're saying, well, wait a sec, what if I have more than 3 arguments? Again, they have the same error message. I wish they had a different error message for every error condition, but they don't. They have the same error message. And so that third test passes. Now, looking at these first 3 tests, it doesn't look like we're getting very far. It doesn't really feel like the method is being too helpful. But this is, I think, an artifact of the order this particular programmer chose to implement these tests. Imagine if they started with the business logic, you'd feel that you were actually developing productive code and not just printing out the same error message over and over again. Nonetheless, we have 3 tests. They're all run. They all pass. Test number 4. In this case, it's still an error condition. And one of the stipulated requirements of the program was that the input should be in the range of greater than or equal to, 10 to the power of 9, between plus, I believe it's between positive and negative 10 to the 9. So the out of range high value for A, B, and C would be 10 to the power of 9, which is a billion, right? So, okay, so A, B, and C must be less than 10 to the 9. We'll note that the expected result is an error message saying A, B, and C should be less than 10 to the 9, or A, B, or C should be less than 10 to the 9. So we run the test, and okay, the first test, second test, third test are all run again. They all pass, but the fourth test fails because we don't have any error handling for the value ranges of the variables. So finally, the programmer has to write some code, and indeed, they have to write code to handle the range of the values, but they also have to add code for the error handling of the number of arguments from above. So now we have basically 4 test cases and 4 passing tests. So we basically have to create the next test and the next test incrementally. They chose out of range low. Now this is logical, out of range low. And if it's out of range low, we get another error message. It's a different one again. Okay, so it runs the test, passes the 4 previous one, fails the new test. The new test fails. Okay, we have to write some code, which is going to look now at the values of A, B, and C to see if they're within the target range. And now the 6 tests pass. So no arguments, less than 3 arguments, more than 3 arguments, out of range high, out of range low, all pass. So now we have, I guess, pretty robust error handling for at least the number of parameters and the value range of the parameters. Test number 6, finally, we're at business logic. So here we have a polynomial which has 2 distinct real roots, with A is 1, B is 5, C is 6. And according to the math of this student, the expected result is -2, -3. We run the test. It fails. It actually fails with the Java null pointer exception. It fails because there's no code handling any math whatsoever there. So finally, we have to add the quadratic equation. If you remember the quadratic equation, the square root of b squared minus 4ac is, I believe that's in the denominator. The numerator has got what is this? So the denominator is 2a, and the numerator is minus b plus or minus the square root of the discriminant, which is there. So this is basically the quadratic equation as taught in standardized school in North America. I think it's in grade 9 that you learn this, how to solve a quadratic, and now they pass. So we have finally got some business logic passing. The next test would be repeated real roots, the same root twice. This passes because the equation would be identical in that case, so we don't have a failing test. Now we have a pure imaginary root on the unit circle with b is equal to 0, and this one fails. And this fails because we don't have any complex number handling for imaginary numbers. So they put in basically the basic code to handle that case, and it passes. And the previous tests still pass. So we always run, every time we add new code, we run the old tests over and over again. So if we accidentally break something, we find out quickly. Then we get into the next test, which is, again, b is equal to 0, but this one has a pure real root, and it does indicate this exposes an error, so they fix that. Then we have some sort of checking, let's see, imaginary from in, not sure what this is, but it fails. Runs a little bit of change to the code, how they handle things, and it passes. We get down to a test here saying, what if the arguments are the wrong types? So what if we have strings instead of numbers? This fails. Add some error handling, which makes sure we have numbers in the syntax that we understand, and now they all pass. A equals 0. This is a business logic rule. It should give you a linear equation, but in this case it fails. It's because of the divide by 0 with the 2a in the denominator. So we basically add some code to handle the case of a equal to 0, and it passes. When we get to the next one, a and b equals 0, again, this fails because there's no error handling about the value range of b. So it add a little bit of code about b equal to 0, but c not equal to 0, and it passes. And then we have all 3 equal to 0, and there's a different error message expected, so this one fails. Add a little bit of code to print the appropriate error message, and it passes. The last test in the list was to test the precision, to see if we had 15-digit precision, and remarkably, based on the test that they chose, it passed with no need to change it, and so they didn't have to write any special code to handle the precision of the system. So basically, with 15 tests, the programmers have implemented with TDD a fairly robust command line quadratic equation solver. Now, you might want to talk to a mathematician who's familiar with computational arithmetic to see if we missed any unit tests, any test cases. I certainly am always concerned when I see in code that basically says, is a exactly equal to 0? I'm used to floating point arithmetic saying that a is plus or minus epsilon from 0, so within some range of 0. And here they're doing always absolute checks for 0. I would say that you might get an instability as the number asymptotically gets closer to 0. So I might have some tests saying, what if the value is 0 plus epsilon, where epsilon is the machine epsilon for Java implemented on whatever the technology is that this is running on. So that's not in there. Still, nonetheless, the same approach would be you'd add test cases, get it to fail, add the missing code, and continue. And always, whenever you add any new code, you regress against the old tests. So we repeat them all automatically. In the end, you generate one heck of a nice set of automated unit tests to exercise the code that you just created. And you're guaranteed that every line of code has at least one test associated with it. So with that, I want to thank you. That's my example for the PolySolve implemented with test-driven development. Have a very good day.